Hello, dear viewer. In this video tutorial, let us solve a numerical on heat transfer in composite sections with reference to finite element analysis. I am Mr. Sukeshian, Assistant Professor in the Department of Mechanical Engineering, SDM Institute of Technology, Ujre. Let us look at the question. Yes, this is the question. A composite slab consists of three materials with the thermal conductivities 20, 30 and 50 watt per meter degree centigrade with the respectively thicknesses 0.3, 0.15 and 0.15. The outer surface is at 20 degrees C and the inner surface is exposed to a convective heat transfer coefficient of 25 watt per meter square degree centigrade. There is also a medium flowing on the surface at 800 degrees C. Determine the temperature distribution in the volume. So probably this is how we can picturize this. There are three walls of thickness as mentioned. The outer surface is at 20 degrees C and inner surface there is a convective heat transfer coefficient as well as a medium at 800 degrees C. Convective heat transfer coefficient we will mention with H and the temperature T infinity at 800 degrees. This is probably a typical application in industry furnaces. The insulation of three layers, you can observe the value of conductivity. The lower value of conductivity states as a kind of insulation. When we observe the picture, throughout its length, the scenario is the same. The heat transfer, it is a steady state heat transfer and the heat transfer pattern is the same throughout its length. Hence, probably we can consider this as a one-dimensional heat transfer. The given parameters as listed, the thermal conductivity of three different materials, temperature at one surface, the outer surface, and the convective heat transfer coefficient as well as the medium temperature. To find the temperature on interfaces as well as the surfaces. Okay, so this is a two-dimensional picture how that is which can be represented. The one-dimensional finite element model of this can be written like this. It has three elements. The three layers of composite material can be represented as three elements with the node numbers 1, 2, 3 and 4 which will constitute three elements. Let us proceed further. So our aim is to write the equilibrium equation, find out these parameters and solve for temperature. The equilibrium equation for this condition will be written as the matrix K, stiffness matrix, into temperature matrix plus the convective heat transfer coefficient into temperature matrix must be equal to force vector. The element stiffness matrix can be written as, the formula is known for us, K is equal to conductivity into area of cross section divided by element length into 1 minus 1 minus 1 1. This is already we have derived and learnt. We know the parameters as well. Let us proceed for element 1. For element 1, the stiffness matrix can be written as K1 A1 by L1 into 1 minus 1 minus 1 1. It's a 2 by 2 matrix. When we substitute the values, it is 20, the conductivity of first material, into area of cross section, which is not mentioned in the question, so let us consider it as unity. And element length is of course given 0.3 meters. So when we simplify this, we will get a matrix of as shown in the screen. Similarly, if we continue that process, repeat the process for element 2, it is K2 A2 by L2 into 1 minus 1 minus 1 1. When we substitute the values, K2 is a 30 watt per meter degree centigrade and the thickness we know, the element length is 0.15. So the value comes to be around 200 as mentioned on the screen. Let us do it for K3 as well. the element 3. So our next aim, as we mentioned, as we observed in the equilibrium equation, this is a global stiffness matrix. What we have found is element stiffness matrix. We should assemble this and we should get the global stiffness matrix. Alright, so we know very well how to find out a global stiffness matrix when the element stiffness matrix is known. So as shown on the screen, for element 1 we have node number 1 and 2, for element 2 it is 2 and 3, and for element 3 it is 3 and 4. And from the free body diagram, what we can understand is there are 4 nodes and each node has 1 degree of freedom, hence the global stiffness matrix size must be 4 by 4. Okay, so let us write the global stiffness matrix. You can observe in the screen. As we can observe in the screen, the global stiffness matrix, it's a 4 by 4 matrix. So in the first column and first row, second column and second row, till these 4 elements are as it is. These 3 elements are as it is from the first element. The second row, second column and second row, the element which is represented is an addition of the number second row, second column of the first element and second row, second column, the number as we shown in the screen. The addition of these 2 elements will give this element 2 by 2. Similarly, we will have an addition in the 3 by 3 column as well. So this represents global stiffness matrix. We have already practiced so many examples on global stiffness matrix. So our aim, as we have seen, we have found the global stiffness matrix. The temperature matrix, of course, it is known. We should find global stiffness matrix with reference to convective heat transfer coefficient as well as force vector. Global force vector we need to find. So let us proceed for convection conditions. Convection condition is only at node 1. The convection condition is only at node 1, which is given by, we have the defined formula, H is given by A into H into 0. When we substitute the values, area of it's a unit area and H is a 25 watt per meter square degree centigrade, and this is the matrix what we get. Similarly, if we write the force vector at node 1, we have only the temperature condition at node 1. If you write the formula, we know it is F is given by A into H into T infinity into 1, 0. If you substitute the values, area is unit area and H is 25 and T infinity is 800. So we will get it as 20 into 10 to the power 3 and the other element is 0. So let us write a global convective matrix as shown. See, we can observe, as we can observe in the free body diagram, only node 1 has got the convective condition as well as the temperature force vector. So hence all the other nodes will have 0 values. So we can write the global convection matrix as represented on the screen. Similarly, the force vector, it is only there in the node 1. The force vector value is given only in the node 1, that is 20 into 10 to the power 3. All the other nodes will have 0 values. So if you write the, if we substitute this into the equilibrium equation, these are the data we have. When we substitute this into equilibrium equation, we can see on the screen. We should multiply it and we should add the matrix, and when we simplify, probably we can find the values of T1, T2, T3 and T4. It is already known 20 degrees it is given. So when we solve using either calculator or maybe in terms of equations, we will finally reach to these numbers, where T1 is 305.25 degrees C, T2 is 119.72 degrees C, and T3 is 58.075, T4 is given value 20 degrees. To solve this, either you can follow in the fourth row and fourth column, there are only two values which will give a relation between T3 and T4. So, if you find a relation between T3 and T4, T4 is known. So, T3 also you can find. You can change the equation in the third row and we can reduce this 4 by 4 matrix to 3 by 3 matrix and you can find out the values T1, T2, T3. I hope you have understood this. Thank you for watching.